Today we are going to discuss about DC machines. Okay, the common name is given to DC generators or DC motors. DC generators and a DC motors. Common name is given, that is DC machine. The reason is construction wise both are same. Generator means we know. We give mechanical input, we will get electrical output. This is for generator case. If you consider motor case, we give electrical input, you will get mechanical output. This is a motor case. The construction wise both generators and motors both are same. See, for any DC machine we have a shaft, we have a load terminals. If you are giving the input, electrical input, and if you are taking the output here, giving the input here, and if you are taking the output here, then this is a motor case. If you are giving the input here, input to the shaft, and if you are taking the output from the electrical terminals, then that is the generator case. So since the construction wise generators, motors, everything construction wise everything will be same, and since they operate on DC because the supply is DC, they are called as DC machines. A common name is given. Now we'll discuss some of the basic terms. That is first flux. Flux is nothing but the amount of magnetic field around a magnet represented by lines of force. Amount of magnetic field around a magnet represented by lines of force. So we'll take a magnet, North Pole, South Pole. Every magnet will have lines of force around it. They are closed lines inside. These are what lines of force. These are lines. These are nothing but the lines of force. Okay. Now it is represented by the symbol pi. Units are webers. And always the lines of force emerge from north. Pole and enter into south pole. Okay, this is entering into south. This is one more point. Let us suppose the total flux lines, the total flux is pi. Then this portion, the above portion is pi by 2. The below portion is pi by 2. Okay, half of the flux above and half of the flux below. Next, flux linkage. So it is nothing but the interaction between the flux and the conductor, or the conductor and the flux and conductor. How they are interacted, how the flux and the conductor are interacted, or conductor or flux, anything. How the interaction between them, that is called as flux linkage. Means flux linking with the conductor. Now, flux will be two types. One is time invariant flux. Means constant flux. With respect to time, it is not varying, so it is a constant flux. DC flux we call this also DC flux. There is one more flux that is called time varying flux, alternating flux. Time varying flux, alternating flux. So this is called DC flux, this is called AC flux. Now we'll see how the time invariant flux DC flux will link with the conductor, how the time varying flux AC flux will link with the conductor. For time invariant flux, if it has to be linked with a conductor, means that if the DC flux has to be linking with a conductor, then either of them, any one should be moving. Let us suppose in this case, in first case, flux is moving, conductor stationary. In second case, flux is stationary, conductor moving. So people call this one as a relative motion. Between flux and a conductor. Either should be a relative motion between flux and conductor. See, for a time invariant flux to be linking with a conductor, a flux linkage to happen, there are two cases. The time invariant flux, the DC flux, is to be moving, conductor stationary. Here there is a relative motion. Which one is moving? Flux is moving. Here there is also relative motion. Which one is moving? Conductor is moving. Relatively, either of them should be moving. Okay. In these two cases, the flux linkage happens. Okay. Now next we are going to discuss about time varying flux. How time varying flux links with a conductor. Time varying flux automatically links with a conductor. There is no need to be either anyone is moving. Automatically links with a conductor. Links with a stationary conductor. Neither of them should be moving. There is no need for any of them to be moving. It automatically links with a stationary conductor. Okay. So if the flux is time invariant flux, DC flux, either of them should be moving. Either flux should be moving or conductor should be moving. If the flux is a time varying flux, it automatically links with the stationary conductor. Okay. We'll see Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Okay, what he says that for any conductor, let us suppose some flux is linking with this conductor. Some flux linking with this conductor. If the flux linking with this conductor changes, then automatically EMF will be induced. That is what Faraday said. Okay, EMF will be induced. See, this is magnetic thing, flux linking with conductor. If the flux linking with the conductor changes, if it is changing, then automatically EMF means electrical term, EMF will be induced. That's why it is called electromagnetic induction. That is why it is called as electromagnetic induction. If the path is closed, let us suppose EMF is induced in a conductor. If the path is closed, this EMF will generate a current. That's it. If the path is closed by some load. Okay, so it's a simple thing. Maybe this induced EMF, it is occurring because of the flux linking with the conductor. The EMF is directly proportional to is directly proportional to rate of change of flux linkage. It's directly proportional to rate of change of flux linkage. This is called as flux linkage. N pi is nothing but flux linkage. Flux linkage. N is the number of turns. Normally we have taken one conductor. We have taken which? One conductor. Turn is nothing but two conductors. Two conductors. This is one turn. If there are like n number of turns, then we call that one as N. Okay. Now, n number of turns into flux. That is called flux linkage. So this is the equation. EMF is equal to d pi by dt into N. See, I discussed that time invariant flux, otherwise called as a DC flux. I will take an example of DC generator. DC generator. We'll take two poles. Two pole machine. Yeah. Now we know the flux will originate from north pole, enter into south pole. Yeah. Okay, it's a which flux? It's a constant flux. It is a which flux? It is a constant flux. A time invariant flux. Every magnet will have some rating of flux for that. Okay. Now it's a constant flux. It's not varying. Now see. Let us suppose you keep a drum. Inside the drum, you keep a conductors. You keep a conductors. Okay. Keep a conductors. For my consideration case, I will be just talking about this conductor. Okay, this conductor. This is my reference. Let us suppose I am just talking about this conductor. Now, see, there is a shaft here. I have given my mechanical input. Means I am rotating. I am rotating in this direction. Now, if this is moving, the flux linking with this conductor. I am talking about this conductor. At first position it will be here. Next position it will be here. Next position it will be here. Next position it will be here. It will take different positions. Once they are rotating. Now what is happening? The flux, if you take this position, some 2-3 lines are crossing. This position, less lines are crossing. If it is this position, some more less lines are crossing. Like this, it will happen. Like this, it will do. Now what is happening? The flux linking with that conductor, the question mark conductor, the flux linking with that conductor is changing. The flux linking with that conductor, question mark conductor changes. Then automatically what will happen? EMF will be induced in that conductor. This is what we discussed in the first case. What is that? Conductor rotating, flux constant, flux stationary. Conductor rotating, flux stationary. That's what we discussed in the this one. Flux is stationary, conductor moving. This is how flux linkage will happen. Okay. Now if you just understand, the EMF induced will be proportional to what? The EMF will be induced proportional to what? Flux linkage. Rate of change of flux linkage. Rate of change of flux linkage. Okay. Now we'll see the second case. Same, that is time invariant flux. Time invariant flux and conductor. In this case now, this is moving. Time invariant flux is moving. Let us suppose north pole, south pole. I will be keeping a conductor. There is a drum. There are a lot of more conductors are there. They are connected like this. We'll see in the next classes how their connections are. Now, just observe in this case what is happening is flux will be moving like this. It's a constant flux, time invariant flux. Okay. Now if you just observe, now in this case Time invariant flux is moving. Flux moving means what? Flux moving means what? Poles are moving. Now this pole is moving. This pole is moving. The poles are moving. Let us suppose this is North Pole, this is South Pole. Next, this is North Pole, this is South Pole. Next, this is North Pole, this is South Pole. Next, it will be like this. Now, if you just observe, if I am talking about only this conductor, if my concentration is completely towards this conductor, at this one, more lines are passing. In the second case, when this move like this, how the flux lines will be? Like this. Less number of flux are touching. There are no number of flux are touching. Again, less number of flux are touching this conductor. I am talking about only this conductor. So, whenever the flux is moving, again, the question mark conductor, this conductor, the flux linking with this conductor changing. Again, EMF will be produced. Again, EMF is equal to N into d pi by dt. That's it. So this is how a time invariant flux and conductor, the flux linkage will happen. Either of them should be moving. Either the conductor should be moving. That is what we discussed in the this case. This is the example is nothing but a DC generator or a DC motor. DC generator and DC motor, we follow this one. The conductors are moving, flux is stationary. This is nothing but we use that one in synchronous motors and synchronous generators. Okay, synchronous motors and synchronous generators. This is what time invariant flux moving, conductor stationary. The conductor is stationary. If my next priority of this one, I will be again, this will be at this position only. The flux is moving, that's it. Okay, this will be useful. This we will be discussing in synchronous motors and synchronous generators. The flux is moving, conductor station. Okay, now whatever the EMF induced will give one name. Whatever the EMF induced here, we will give you one name that is called dynamically induced EMF, because dynamics are happening, either of them is moving. So we call this one as dynamically induced EMF. Even in this case also, we call this one as dynamically induced EMF, because either of them is moving. Dynamically induced. Okay, next we have seen one more flux linkage, that is time varying flux. Time varying flux. That is nothing but alternating flux. AC flux, alternating flux. For this, there should be no movement. Alternating flux automatically links with stationary conductor. We know which machine is not rotating machine, that is nothing but a transformer. Transformer doesn't rotate. We'll see. I'm not going deep into how the transformer operation will be. I will be just giving you what is happening in this case. Okay. Now see. First, I am giving here a coil. Is n number of turns. I am giving an AC supply. AC voltage, AC current. Okay, AC current with n number of turns are there. Okay, n number of turns, and this current is what? AC current. This is called as number of turns into current is called as MMF. MMF means magnetomotive force, just like EMF. What will EMF will? EMF will drive current, will give out the current if the circuit is closed. Just like that, MMF will drive flux if the path is closed. So this will produce flux. Tell me, this will produce flux. Now tell me, the current is an alternating current, means changing current. The flux is also what? Changing flux. Means since it is alternating, the flux is also what? Changing flux. Actually, flux formula is pi. Pi is nothing but flux. Flux formula is MMF by reluctance. Just like current formula, voltage by resistance. Voltage or EMF. EMF by resistance. Resistance means what? Opposition to change of current. Reluctance means what? Resistance means what? Opposition to current. Inductance is nothing but opposition to change of current. Opposition to current. Reluctance is nothing but opposition to flux. MMF will drive the flux. Okay. EMF will drive the current. Now since the MMF is alternating, reluctance is a constant value, the flux will be also alternating. Now just observe this. I will tell you. Just observe this. Means what? The flux is what we got? Changing flux. Now this flux, okay, n number of turns, the flux linking with this conductor or these turns is changing. So what we know according to Faraday's, any flux linking with a conductor changes, EMF will be induced. Then here EMF will be induced. Okay, if I keep a second winding here, the flux will be flowing like this. The flux will also linking with this conductor. The conductor is stationary. Here the conductor is stationary. Again here also EMF will be induced. So transformer action, I'm not completing the complete thing. So transformer action is nothing but, so time varying flux, alternating flux requires stationary conductor only. Even with the stationary conductor it will link. Simple logic. The logic is Faraday's law. The Faraday's law, what it says, the flux linking with the conductor changes. The flux linking with the conductor changes, EMF will be induced. So already the flux is alternating flux. So it will come, if any stationary conductor is there, the flux linking with that conductor is already changing because it's an alternating flux. So for that, no need of movement. That is what transfer. So hope you understood this flux linkages and everything.